Yeah, thanks very much, Peter, for arranging this, and thanks a lot for coming in the last minute. I happened to be in town. I wanted to see CWI, and Peter politely invited me to give a talk, so here I am. So nowadays, there's only one thing that I talk about by going around the two different groups. I talk about Kuzu, which is this new graph database management systems that's meant to be like DuckDB but optimized for graph data management. But I kind of assumed that I had given a talk in Amsterdam Insider earlier this year, and I had given a talk related to some of the query processing techniques about Kuzu in the Dutch seminar, this seminar basically before. So I thought, that might be boring and people might be familiar. So I'm going to give a very technical talk about a VLDB paper that we published last year on cardinality estimation. Anybody who works in the space long enough is destined to take on this topic. Do it once and then move on and never return. As you'll see, it's an impossible thing to actually sort of crack. But this is my take on it. And this was an experiments and analysis paper. And part of the contribution, as you'll see, is a bit kind of educational, trying to kind of reinterpret several of the existing cardinality estimation techniques in a new lens. So there'll be a very simple framework to look at it, which we got to by kind of trying to understand a particular problem, which is that often when you try to estimate the cardinality of a complex join query, there's multiple ways you could put statistics together. So what is sort of a good way to understand the space of ways to put things together? Because that's what cardinality estimation graphs will be about. So this is a lie. I think I'll only be able to talk about cardinality estimation graphs, but if I get time, I'll give you maybe 5-6 slides on the overall vision of Kuzu as a second part, right? So let's get to it. All right, so this is the problem that I'm looking at, cardinality estimation. So your database engine gets a query as part of plan generation, often as part of the part of the optimization or plan generation where you try to pick a join plan. You need to estimate the cardinalities of the query and possible different subqueries within the query as you're enumerating the plan. Again, I'll be focusing on natural join queries, and I come from a graph database kind of perspective where join queries are essentially trying to match patterns, but they're equivalent. Okay, so I'll you're not going to lose any kind of accuracy when I move to the graph space. Exactly the same problem any system faces when optimizing complex joins, right? So the most obvious, I shouldn't say obvious, the most popular way people have implemented cardinality estimation in systems is these statistics-based or summary-based techniques. So this has two core ingredients. It's very widespread. Now, the first thing that the database does is that it stores some statistics about the database that it's managing, right? So maybe you got these two tables, employees and projects, and common statistics you might want to store. It's kind of universal as number of tuples. Every system kind of stores this in its catalog, right? And then a lot of different approaches to store different statistics about the value distributions in different columns. So if you focus on this one column, for example, one common statistics that I've seen systems store is the number of unique values in the column, because it's one statistic you might want to store and use it as you're estimating the cardinalities of different subqueries. A second one is the maximum degrees. A degree here means the maximum number of times any value appears, right? So that's a degree, although I'll define this more formally later. That's another statistics systems might store. A system like Postgres stores value distribution histograms. So you get a kind of you store kind of a sequence of statistics about the column. Or as I will tell you from the world that I come in, where for graph database management systems, and I'll make this connection a bit more concrete, at least kind of the academic work that's being done in graph database management systems, one common statistics that they store is size of small size joins, maybe like 2 paths or whatnot. Okay, so and that will be important, and I'll come back to this. Right, so that's the first ingredient. The second ingredient is that the stored statistics will be put in some kind of formulas, very simple formulas, to come up with an estimate for the subquery that have kind of universally two properties that they make: uniformity assumptions and independence assumptions. And let me give you an example. So suppose you have this query, you're joining 3 tables, and I picked this because these binary tables are going to be exactly how you'd model sort of the edges of graphs. So that's how I'm going to move to the graph world. But I've got three tables A, B, C, and this would be an equivalent SQL version of a two-path query over three edges, three-edge query with two join conditions: A.dest is equal to B.source. Suppose this is query. You know, a dynamic programming-based join optimizer, which is very commonly implemented, would enumerate two-size joins. So it's essentially find a plan for the subquery AB and find a plan for BC. You wouldn't find one for AC because there's no join condition there. There would be Cartesian product, and the optimizer is going to pick a plan, and then along with the plan store the estimated cardinality of these joins A, B, or BC. And one example formula that I've seen implemented across several systems is something along the lines of: you take the min or max, okay, you can decide this as the developer, of number of tuples in A multiplied by number of tuples in B divided by number of distinct tuples in B.source, right? So, and whenever you see this multiplication, that's where your formula, in your formulas, you're making an independence assumption. And I'll interpret this. And whenever you see a division, that's where you're making some kind of uniformity assumption. So let me interpret this. This is what this is really saying. It's kind of similar to formulas of conditional probability in elementary probability. Each A tuple is going to extend to essentially number of B over number of distinct B.source many tuples. And why is that? So intuitively, if there's 100 tuples in B and there's 10 distinct values, it's making a uniformity assumption that each value appears 10 times. So each A value independently, that's where you make the independent assumption, that's the multiplication, is going to extend to 10 B tuples. Okay, that's the uniformity assumption. Obviously, if the number of distinct B.source tuples is 10, it could have been distributed in a lot of different ways. It could have been like one value takes 90 of the tuples, and the other sort of 9 takes the rest of the 10 tuples, right? It's not making any of those complicated assumptions. It's essentially making that, let's assume the simple thing that is super uniformly non-skewed, basically, distribution on the column, and we'll make that uniformity assumption, and that's the independence assumption. That's our estimate, right? And similarly, you could have done the other way. You could have said number of each B tuple is going to extend to A over number of distinct A.destination tuples. And then you take the minimum or maximum. So formula along these lines, right? And when you enumerate the dynamic programming optimizer, enumerates the larger subquery ABC, it's going to use these estimators and the plans to come up with an estimate for the larger query ABC here, using a very exactly the same formula, changing some numbers. Essentially, it's going to say each, for example, over here, each tuple that comes from the AB join, which is there's est1, many of them, will uniformly extend to C over this distinct C.source values, so on and so forth. And this is going to be kind of the spirit of the formula that's being used, making uniformity and independence assumption and using the statistics that are stored. Here's a second example from the world that I come in from. Graph databases, they perform joins over edge records. One advantage that this has is that when users essentially define their database, they tell you that these A table or these A records are edges, which means joins are going to happen over them. So the system can look at the kind of the schema and know the common joins that will happen. So it gives it an advantage to know a priori the common joins that will be executed. So it can store statistics about a join of AB or join of CA or join of EA, so on and so forth. And this is common across the work that implements graph databases, that along with maybe statistics over the base tables, they will store statistics about the small size joins, right? So here's actually 4 examples from literature. GraphFlow, we also implement, this is a system that kind of the precursor system, Kuzu. We had implemented something like this. So here's a 5-edge join in this cipher syntax. So a common sort of set of statistics that will be stored is the system is going to store in this catalog the sizes of these small size joins, and I'm calling this a Markov table because it's the earliest example that I know from the XML world, where this is from, I think, early 2000s, 2001, where this catalog was called the Markov table. and I'm kind of giving the credit to the earliest work that I'm aware of. So you'll store these ABCs, BCDs, BCs, sometimes triangles, not in XML world, but for example, in GraphLoad, we were also storing small size triangles up to some size, and H is the size up to 3. And then the formulas are just going to look extremely similar. To estimate the size of ABCDs, the formula is going to be again inspired by elementary conditional probability formulas of number of ABCs will uniformly extend to CD over C or something along these lines. Okay, this is kind of saying each C is going to extend uniformly to CD over C many CDs. Okay, something along these lines. So here's the problem with optimistic estimators. The first one is that
it's a question about that.
Sure, yeah.
So is that because you can't use unique distribution of CDE? Is that hard? Like, why don't you have the equivalent number you'd have normally?
Unique distribution of CD, like
so
unique
if there will be a
distribution of
table,
what exactly?
if I understood you correctly, you will take the cardinality of the table divided by the number of unique values.
So CD here is a join, actually.
Right.
It's not, so you can think of it as a table, but it's
right.
the table of the join.
Right.
Yeah.
So if this will be a table, you'll have the cardinality of the table at top divided by the number of unique values in the bottom, right?
That's right.
Right?
Yeah.
So why is that not equivalent? Like, why don't you have a number of unique values for CDE join?
Number of unique values of what exactly in CD? So CD is a table,
Right?
Right.
So of oh, okay.
So it's got 3 columns, C and D and E, unique values of. So you could use other statistics. Oh, okay. Is there the answer? No, so you could use other. Okay. All right. Okay. Any other questions? Right. Come. Okay. Very common, okay, uniformity, independence. We have one problem that's very well understood right now, and I think well appreciated, is that this leads to large underestimates. Why is that? Because first of all, the uniformity assumption is optimistically and without no justification, assuming that there is no skew, right? That's not realistic. And second, the independence assumption, which you're multiplying, quickly compounds, and compounding things quickly kind of go to extremes. Right, so this is a paper, actually, Peter is a co-author of this paper that I think has very well demonstrated this, that, you know, systems kind of broadly suffer from these optimistic cardinality estimates, and because they use these formulas when they implement them, right? So that's one problem. The second is that this is, I think, less appreciated is, and this is where kind of, this is the problem that we focused on in this paper, is that there's often multiple combination of statistics possible to estimate the cardinality of exactly the same subquery or query, right? So for example, if you have a star query ABC, and you suppose you stored all sort of small size joins, sizes up to 2 or 3, doesn't matter. Here's one formula you could use: number of ABs times number of BCs over Cs, right? Or you could say number of BCs times number of ACs over Cs, and these are different formulas, right? So it's AC, BC are different. So AB, actually, sorry, BCs are the same. AC, AB is different. Cs are the same, but these are different. Okay, so you're going to get different statistics. And another one is something like this. You've got 5 size joins. Here's one formula that I already showed you: number of ABCs times CDs over Cs, where you make the uniformity assumptions. Or you could be using, if you got statistics up to size 3 joins, ABC times BCD over BC, which estimates ABCDs. And then you can think of ABCDs extending to ABCDEs with this formula, CDs over CDs. Okay, that's another formula, right? So, you know, one of them is kind of making one independence assumption. So there's one multiplication, but arguably, although I don't want to say something very strong here, if you looked at this, you might expect the uniformity assumption that this first formula is making to be more aggressive, because it's kind of assuming that each C tuple is going to extend not only uniformly to all Ds, but also to E's, right? Whereas over here, you're making 2 independence assumptions, 2 multiplications, but arguably, again, making less aggressive uniformity assumptions. So assumptions that are maybe more likely to hold, because you're saying, like, to extension to, so maybe CD is a better example. The extension to E's only needs to be uniform over CDs, not even C's. Okay, so it's kind of unclear. So this is the problem that kind of motivated this work, was like, there is often many and depending on the shape of the query, the formulas kind of are different. The number of formulas you could use are different, without a kind of a clear sort of choice, which one should be used, okay? All right, so the questions that we kind of studied are, first of all, what is even the space of all formulas? You get a complex join query, what is the space of all formulas? How should one think of the space of formulas? Second question is, once you've understood the space of all formulas, what's the space of heuristics to pick a formula to use when there are multiple options that you could use? And the third one, the important question is that once you know the space of heuristics, which heuristics should you use? Which heuristics works better in practice? And the last one, the most important question, obviously, is what statistics should be stored, right? This is the most important question. I'm not even going to bother trying to answer that. I don't think it's answerable, but let me just tell you what I'm going to deliver. I'll give you a very simple way of thinking of all these space of formulas. I'll think of it as a lattice or a graph we call the Cardinality estimation graph. For optimistic estimators, the ones that use these uniformity and independence assumptions, I'll show you 9 very, I think, intuitive heuristics to use. And then I'll give an advice, empirical advice on which one to use. And that will depend a little bit on the shape of the query. Okay, but for the most important class of queries, which are acyclic queries, I'll make the advice that you should use the pessimistic formula, the one, I mean, hopefully it's already intuitive, that because we suffer these estimators suffer from aggressive optimism, that you should try to offset it with by picking sort of formulas that are more pessimistic in their estimates. Right, so it's going to be delivered in this. Okay. So any questions? Good. Right. So here's the simple framework to look at cardinality estimation graphs. So this will be a lattice where vertices are going to be the subqueries of the query, and edges will be essentially some weights that indicate how a smaller subquery extends, the rate at which a smaller subquery extends to a larger subquery. So indicating this independence assumption, the multiplications that are going to happen, and each bottom to top path is a formula estimating cube, right? So here's essentially an example. We will have subqueries. I'm assuming we're in this case, I'm going to assume, and this doesn't have to be the only cardinality estimation graph you could have for this query, but I'll assume that you store up to 3 size joins. So ABC here, there's a little typo, so I should indicate that this is an ABC path, but I hope that that's clear because everything is moving left, moving right. These are these different, essentially, subpaths or subqueries in the query, and then there's different edges indicating the rates at which they can indicate. Okay, that's it. That's what a cardinality estimation graph is. You could define different estimation graphs, cardinality estimation graphs, by picking different statistics and putting on these edges as weights. Right. So here is the one that's been used by these, at least 3 of the 4 references that I showed. From the graph database world, where we have these subqueries, and I'm assuming we got these Markov table or a catalog that stores up to 3 size joins. For the bottom layer, we're storing exact statistics. We know exactly how many ABCs there are because we've stored them in our catalog, and everything else is where we make uniformity assumptions. So BCD over CD makes a uniformity assumption. It's essentially putting average degrees of values into this cardinality estimation graph as weights, right? And a formula, the first for my running example, is the path that takes you from the bottom empty set to ABC to ABCD. That's one formula. And this other one that I showed where it was unclear which one was better, that's motivating question, is this formula that starts with blue and takes the green path. Okay, that's a good way to think of the different sets of formulas, right? So what is the space of heuristics? So an estimator is essentially, like when you implement this in an actual system, you need to make a decision about which of these formulas to pick. It's essentially just a heuristic for picking path. And I think an intuitive way of defining a space of heuristics is along these 2 questions. First of all, the first question you need to answer is that which paths are you going to consider in terms of the length of the path? right? So you could essentially pick paths that are short in hops, so 2 length paths, or you could say I'm going to pick paths that are long in the CEG, so longer paths, so 3. So here you need to make a decision between 2 or 3, basically, for this query. Okay, so that's along one direction, or you could say I'm not going to make a decision, I'm going to consider all the paths, and each path gives you a possible estimate. And once you have a set of estimates, if you've limited them by the number of hops, now you need an aggregator to decide which one of them to use. So you could use, for example, the maximum estimate that they make, or the minimum estimate that they make, or you could take all of them and take the average, right? So something along these lines. I think this is kind of this 9 space is a good way to understand the space of heuristics that you could make. Essentially, the 2001 paper was making this max hop estimate and was unclear about which one to use in terms of the aggregator. We used the min aggregator in GraphFlowDB, and we were not clear on which hop we picked because it was based on kind of the behavior of our dynamic programming optimizer. So it wasn't really it was a little arbitrary. But whenever we were at this position, we made the optimistic estimate. We were picking the min aggregator. And this graph summaries was, I think, sort of unclear in both of these. So they didn't acknowledge this problem actually existed. Right. So let me show you which one works better. So on acyclic workloads and cyclic workloads with small triangles, but you can ignore that. But let's focus on acyclic workloads. We looked at a bunch of sort of benchmarks in literature. Join order benchmark is the one that was used in this Leys et al. Paper that Peter is also co-author of, that established that cardinality estimation is the important thing in optimization. We kind of turned those into graph queries. There's a couple sort of other benchmarks that were defined in prior work related to sort of path queries or different graph pattern queries. And we also had our own on several other data sets to look at which one works better. So here on the x-axis are the different 9 estimators. I'll tell you a little bit about P star. And they're in the form of the hop heuristic and the aggregation heuristic. Something like max min says we're looking at the longer hops, okay, making more independence assumptions, but hopefully less aggressive uniformity assumptions. And then we're being optimistic and picking the sort of the lower estimate out of those paths. Right? So out of these, the one that, again, there's never going to be a heuristic that's always good. It's very easy to show cases that any heuristic will be just for any particular query. You can define for any particular, there's going to be a query in which any of these heuristics just shine. But broadly, if we look at kind of the results that we're getting, over here, I should also explain this. This is the Q error, sort of kind of the scale of the mistake, accuracy mistake that these different heuristics are making. And minus means that it's underestimating, and plus means it's overestimating. So that's why you see both numbers in the plus and minus. But something that kind of clearly came up is 2 things. Be pessimistic, so pick the max aggregator, right? With that, I hope is intuitive. And also make more independence assumptions and pick the longer paths. Make more independence assumptions, so compound, but you can but make better, arguably better uniformity assumptions. Okay?
Yeah, the question is, so because how was this evaluated on the IMDb? Because like actually the job paper, and which thanks for mentioning, that is doing IMDb, but it also of course has filters.
Yeah,
and that's a whole different space. How filters will interact with your estimates. So it can be correlated filters.
That's right. Yeah.
So this was without filters.
This was without
filters.
filters.
Unheard of in job. Job. Like the errors are all over the place, and getting to a Q error of 0 is like a dream.
Yeah, so it is without filters. So we remove those. It is without filters. That's right. Just the join part of the query. I mean, the entire paper is about kind of estimating the joins.
Yeah, sure.
Right, to simplify things. You're right. But again, so we are across a wide sort of range of benchmarks, this is really consistent. Max usually just consistently performs better to estimate the join part, right? So when you include filters and whatnot, the paper or this framework gives you now advice about how to incorporate those. That's a good point. Yeah.
Okay. May I ask a question? Quick question on this.
Yes.
So I'm curious about the properties of that cardinality estimation graph. So the example you gave, the query pattern looks like a path, so that there are not too many joins which are not Cartesian products. So you can put all of them in the same lattice kind of image. But in general, the number of those subsets which have non-trivial join conditions, like how big that can be, and like how scales that thing?
So is the question how complex, how many paths do you get per query?
It's not even paths, like even the nodes, like you see here you have like A, B, C, B, C, D. So those are the subqueries, like joins which are not Cartesian products, right?
That's right, you're right.
But in general, the number of these nodes, like if you have like cyclic queries with like multiple join conditions, like the number of these nodes, it seems to me like it can grow like
it can grow, yeah, it can explode. So let me give you a good example of where it explodes. Star queries is where it explodes, is the worst case. Like if you've got a 10-star query, you can't actually, it's hopeless to even enumerate all possible paths. It's just the number of sort of different paths you can take explodes. Paths are the best behaved, where your cardinality estimation graph is the smallest. So you're right. So, no matter what, there are some queries that just explode, in which case these heuristics are not going to be enough. So you'll have to fall back down to some greedy approaches. And, there's a section in the paper that talks about that as well. There's even some of our evaluation on some queries, like 9-star, 10-star, we had to fall back to something because the number of paths just explodes.
Okay, thank you.
Yeah, so that's a good observation.
Can I also ask something?
Yeah.
Can you give some intuition as to why the independence assumption wins over the uniformity?
I don't have a clear sort of. So these are two conflicting sort of advantages and disadvantages. So a priori, I didn't have an intuition of which one would be better, but clearly, like from the numbers that we'll get, and for acyclic queries, I mean,
is my question. Like for that case, why is that one better than that?
Yeah, it's difficult to give a very good intuition. I think I didn't know how to answer this question except to run benchmarks and see which one performs better. Again, the way we wrote the paper also was like there's two conflicting sort of advantages and disadvantages, because it also seems like compounding less is an advantage, but apparently it's a sort of a less strong advantage than making better uniformity assumptions. So yeah, that's all I can say. Like, this is, I don't think there is a very sort of deep reason I can come to, but yeah, that's all I can say about it.
It does seem like across the board, like the mean marks doesn't matter, like which path you take, and also the error margins are way narrower.
Yeah. So you're also just to be clear, between the paths, it's also between this number of hops, it's a less of an effect than the aggregator. Aggregator kind of clearly dominates, as you can see. Like this max, these three are the max aggregators. They're clearly doing much better.
Okay. Yeah.
Okay. Within this, you're comparing this box plot and that box plot between max and min. So it's less of an advantage, like less clear an advantage than the aggregator. The bigger message is you speak pessimistic whenever you can. As you're implementing this, even in your dynamic programming sort of optimizer, you're considering multiple paths and you are picking between different plans and whatnot. You could still change your dynamic programming optimizer to pick a plan from one of those subqueries, but pick the estimate from another one. That's also possible. So you're going to be more accurate if it is more pessimistic, right? Because often when you put these statistics together, there is no reason, unless there's some property of the statistics that when your dynamic programming optimizer is kind of enumerating, that the different formulas that's put together are going to be the same. There's no reason for that to happen. And if you're in that situation where you can pick, you can just make that fix that maybe you can have two pieces of code. One picks the plan from the better sort of subquery, but one fixed estimate from the worst subquery. And you can do something like that to offset your optimism a little bit.
And you can say something about the distribution, like, so take the mean or the max. That means that you're influenced by just one element. It doesn't really matter what the other people do, other type. So if you have multiple paths to the graph, right? And if you aggregate to, you said the aggregator is the most important one. Right?
Yeah, aggregators. I
The
think
max aggregator means same, right? It's sensitive to just one element. All the other things can do whatever they want. They stick to the maximum. So if you have a everyone agrees it's one, but there's just one thing that's a 10, then it doesn't really matter how many hopes or how many things you do. That one thing dominates it. So I was wondering if you can say something about the distribution of the.
Did you consider median, for instance?
pick the median, like average is trying to do that, right? Average is trying to pick the so maybe median is just yet another aggregation.
My question is what I'm asking. So this is not sensitive to perturbation in the graph because max is the max.
That's right. I see.
And I was wondering how much diversity there is in opinions.
I don't know. We have the data. I don't know. Although just one thing that I can directly say is that anything other than max or min, I think is going to be very slow to implement.
Yes.
So because you're forcing yourself to look at a lot of estimates.
Yeah.
So if you do, well, yeah. So let me say like max and min have the advantage that you can find paths quicker, and that's going to be important.
Yes.
Right? Okay. Okay. Any questions? All right. Okay. So here's another problem. So the previous example that I showed was, to be very complete, was acyclic workloads and cyclic workloads with triangles. This we meant that you have in your catalog essentially estimates for small size joins, which you can match in the join. In the actual subquery that you're estimating. But sometimes a query like this, if you're like a 4 cycle is the best example. In a query like this, if this is your pattern, so it's actually a cycle, so there's additional join conditions. We also noticed that at least in the papers that were written, they weren't doing essentially something additional to account for these essentially additional join conditions that would close cycles. So basically what we noticed is that, so you get a Markov table like this, right? And you're trying to estimate ABCD, essentially a path like this, ABC times BCD over BC, would use these 3 statistics, and it's actually not estimating a cycle, it's actually estimating essentially the number of 4 paths. So it's kind of ignoring that this cycle was closed. So the formula for ABCD would be exactly ABC times BCD over BC, but that's a path. And there's a lot more paths than cycles. So this was essentially a common thing that is missing, that in the structure in your join conditions, you should have an additional, essentially something extra that's done to acknowledge that some cycles are being closed, because your patterns that you are essentially using to come up with your edge weights, they don't have the capacity to acknowledge that, right? So if that's the case, and if you're going to stick to the traditional sort of statistics that have been proposed in literature, you basically need to become optimistic now, because you're estimating paths whenever there are these large cycles. You're not estimating cycles. So forget about this purple ones, but look at the blue ones. So that's the original cardinality estimation graphs that don't acknowledge these large cycles closing. And in this case, you can see that the min aggregator, I mean, they're doing broadly much worse, clearly. These are harder queries to estimate, but the min aggregators are clearly starting to do better. So now you're overshooting. The fact that you are estimating paths instead of cycles is overshooting. And this was a way that I'm not going to say too much about this, but the path, I can't give a clear advice about this. But in terms of the number of hop heuristic, but if you're using the original CO, you can be optimistic now. And this was a way for us to essentially show that, look, change your statistics and put other statistics that acknowledge that some cycles are closing from smaller subqueries to larger subqueries. So we have these, they weren't like magic constants, but we had these other sets of statistics about certain cycles closing with several patterns. I don't want to argue that that's a good thing, but we just wanted to demonstrate that by putting these other statistics, you don't change the complexity of your cardinality estimation finding paths, but you just store more statistics that acknowledge that some cycles are closing. And if you put those edge weights, now you can again get so essentially offset that pessimism of finding paths. And now again, kind of max starts doing better. Max aggregator starts doing better. Okay, this was just a way to, again, in this spirit of this experiments and analysis paper, to show that like the real question which the paper doesn't answer is like, what statistics do you want to put, right? And then there is options, and so we want to show like, here's one set of options. If this is the problem you're trying to address, here's a set of statistics that we computed, we put them as edge weights, and here we get much better statistics, right? So maybe
a very simple version of that would be to maybe say, if you close a cycle, you should multiply by whatever, 1 divided by the distinct. Well, very distinct, because the chance that you end up in something that's the same if without other knowledge would be that.
That's right. So that's essentially an even simpler version of what we did. This is a bit more advanced statistics, because we don't like, these are a bit more advanced because they take into consideration the sort of the labels of the edges that are actually closing and whatnot. So that was another option. So we also tried that, but because this was better, that's the one that these are the statistics that we proposed. But we also tried that. Okay. Yeah. So one thing I should say is maybe in both of them, there's this P star thing in my slide, which I forgot to mention about. P star is this thought experiment about sort of suppose there was an oracle that looked at all your formulas, and the oracle said, I'm just going to pick the most accurate one. So this is kind of both a study of what is the limitation of this type of estimators. Fundamental limitation that, even if you were to pick the best path for every query because an oracle had this power, that's the distribution. And it serves two purposes: to see the fundamental limitation of these types of optimistic estimators that use formulas, plus how much off are you from that oracle, right? So this is where you'd be, and it's just showing that there's some queries in which, like, whatever you do, you're going to be like, I don't know, 50x, 100x off, and it's even much worse for these larger cyclic queries. Like, no matter what you do on CEGO, look at this P star is just, it's very difficult to estimate like this. There's a fundamental limitation of this type of estimations. Right? Okay. So now I want to take a sort of open a parenthesis to tell you about something that you might find sort of research-wise interesting. There is a set of new estimators. There's a couple papers on this called pessimistic estimators. This has been kind of led by University of Washington, by Dan Suchu's group, Dan Suchu and Magda and their graduate students. The first one came in 2019, and then there's another one, I think, in this segment, where these essentially kind of motivated by this Lace et al. Paper that said, systems are extremely optimistic. They want to use essentially these upper bounds on the size of the queries as estimates, worst case upper bounds. So there's been essentially over the last 10 to 15 years, there's been a development in the theory of worst case optimal query sizes, which answer this question. Basically, you're given a joint query and you're interested in the maximum size of the output. And there's these different bounds using different statistics that you can put that are essentially saying, like, this is the worst that it could happen. Okay, so this was answered. This started in 2008 with a theory paper, and there's been several sort of theory papers along with it. And, there's different kind of these linear programming based bounds. Okay, so what basically these Washington papers do is that they take this theory and they apply it to develop estimators that are guaranteed at least to fix the optimism problem, because they're using these upper bounds, right? So they try to make them practical, right? So let me just tell you a little bit about these, and I'll connect it to CEGs. And I hope, like, this is the part where the contribution of the paper is a bit educational. If you read these papers, I'd argue, and obviously this is subjective. If you read these papers, they might be intimidating. They're very sort of the theories, I don't think, very easy to interpret. But I think like one thing that we were able to show in this paper is that they have a very actually, at least these papers have a very intuitive sort of interpretation, and that's using CEGs again, using cardinality estimation graphs, and I'll show you that. Okay, so here's the notation that I'm going to use. The query is a join over Ri with script AI, the attributes, and capital A is all of the attributes in the query. And this is the notion of a degree that's being used in these in some of these bounds, as well as the papers that use pessimistic estimators. The degree of a value of an attribute X is equal to little xj, this is a specific value, over a larger set of attributes in Ri is essentially the number of times that value appears in the projection of Ri into X union Z. Okay, so let me give you an example. If this is R1 ABC, the degree of 1, A is equal to 1 in AB is 2, because 1 appears essentially extends to 2 different values, 10 and 20. Okay, degree of 2 is 1. The 2 extends only to one value, one distinct value. Right. So it's essentially saying how many distinct B values does A equal to 1 extend to? That's 2. How many distinct B values does A equal to 2 extend to? That's 1. And the degree of a particular column is just the maximum degree of any of the values in it. So degree of A in AB is 2. Right. So it's just basically saying any value, any A value is going to extend at most to 2 different B values. Okay, that's what it says. Degree of A in AB in the particular relation says any A value is going to extend to at most 2 B values in R1. Okay, so that's the notion of a degree. So here's a worst case bound from literature where it's a linear program, right? So there's variables in the linear program. The interpretation of these and some inequalities, obviously. Sorry. The interpretation of these variables is that each variable essentially aims to represent the maximum size of a subquery projected into some set of attributes, right? So, you're trying to maximize it respecting certain inequalities. You're trying to maximize the maximum size of the entire query subject to some inequalities. The first one says that, the empty set is empty. It's actually, it means 1, because these are all going to be kind of like, think of it as like 2 to the 0, it's 1. And this one says that the maximum value of X needs to be smaller than any larger subquery. And then third one, which is the most interesting, that uses the degrees, says essentially, let me see if I have something on this. So it basically says, forget about the E. It basically says the maximum X union, like A may be extended to B, the maximum AB is at most the maximum A plus the degree of A in AB. Okay, so it's very intuitive. It's saying if each A value extends to at most 2 values, 2 B values, okay, the maximum AB value has to be 2 times. These are all essentially, because it's a linear equality, exponents have been, like logarithms have been taken. So if you remove the logarithm, this is essentially Sx times 2. It basically says maximum AB has to be at most maximum A times 2. That's all it says. It's something very intuitive, right? So now let me, so one problem with this, and a lot of this Washington papers, takes these essentially linear programs which require numerical solutions, right? So they are hard to implement, and they try to make them practical, right? So they're trying to essentially, a lot of the contributions of these papers is that how do you take these bounds, and some of them are a little bit more complicated, and then try to essentially implement them without actually numerically solving these LPs. So, but let me essentially show that those LPs actually have a very intuitive interpretation. They're basically saying, in our previous CEG that I showed, we were using these average degrees. The pessimistic estimate, let's go through this thought experiment. Here's an estimate that I could use if I store those degree or the maximum degree values. Instead of storing, BCD over CD, if I said the estimate for maybe BCDE is CDE times the maximum value of B that extends CDEs, okay? And the maximum, essentially, BCD can extend to ABCD is the maximum degree of A in particular sort of, it would have to be in B. But if we change these essentially average degrees with maximum degrees, you can see that kind of by construction, each path becomes an upper bound. Because at each step, you're making greedy and very pessimistic assumption. You're saying each CED is going to extend to at most 5 Bs. Well, that's true because, you know, you've computed the degrees. And then each B is going to extend to at most 2, right? And if you kind of compound this pessimism, you're bound to get an upper bound, right? So what we were able to show, and this is kind of a separate contribution, is that that's exactly actually the solution. So no, sorry, I missed one step. So if you do this and change these average degrees with maximum degrees, right? Now, because each path is an upper bound, then there's obviously a clear heuristic now, which is just pick the shortest path, pick the most optimistic one, because each path is guaranteed to be pessimistic. Like to be the most accurate, you need to pick the most optimistic, the best bound, basically. Now, you don't even have to think of a space of heuristic. There's a clear heuristic that you should use. And in fact, it turns out that's exactly this combinatorial solution to MOLP. So this essentially, this MOLP does not require a numerical computation. So which is interesting to kind of, again, educationally to show that, look, what these Washington papers are trying to do is actually all these ways of trying to solve these make these solutions more practical can be solved with a CEG and finding the shortest path. It's exactly the same solution. So you know, one interesting thing, again, that wasn't noticed before is that MLP is a combinatorial solution, which means there's actually, you could use an algorithm like Dijkstra's algorithm if you want to solve MLP. That's polynomial time. So you don't need to resort to numerical solutions. And we were able to just show that this interpretation of these linear programs is useful kind of to understand these pessimistic estimators. So for example, we could show again something that wasn't recognized, that now, first, one thing is that I already showed you, that MOLP solution, if you believe this theorem, that MOLP is the shortest path on the pessimistic, then it's very easy to show that each MOLP is actually an upper bound. Whereas if you just look at the linear program, and if you look at the original paper, there's like a lot of like a 2-page complex proof to just show that MLP is an upper bound. But I think once you think of it as a CEG, it becomes very clear by construction it's an upper bound. We were also able to show that the Washington papers are actually implicitly solving MLP, so on and so forth, all by interpreting in this framework.
But what about the space? It's very interesting. But what about, like, a CEG is a kind of fixed. I mean, depending on what statistics you have, you get CEGs.
That's right.
So, and you can actually make even different assumptions there. Were they also, like these Washington papers, making specific assumptions? Because in a CEG, you are a bit in a restricted space, of course, because you are guided by whatever stats you have. And that's right. That gives you your CEG. And within that CEG, that is indeed true. But are they more general, or are they also making some kind of assumptions on what CEG they actually have there? So
they have the CEG. They have the CEG with the maximum degrees. But one thing that they do is they have this. So this CEG gives you, no matter what you do, I'll give you an experiment too, gives you a very pessimistic estimate. Right. This is the one where you're essentially going for the worst distribution that maximizes the sizes. Now you're extremely pessimistic. Like this, it's kind of like the same that optimistics on. The optimistic go for the most optimistic case where everything is uniform. This goes for the, like, what is the worst thing that you could hope for? So what these papers, like what the Dansucci papers do is they don't look at it. They take a query, they look at the database, and because these things are very pessimistic, they actually partition the table into many. Each table into many pieces based on the degrees of the values. And then they get many CEGs, they get estimates from each, and they sum them up, right? And that's a way of uniforming things. So like, if, for example, so here's the intuition for what they're doing. If, for example, there's parts of your database where the degrees are very skewed, right? And if you partition your table into uniform and skewed, and you had a CEG for the skews, now you're making a pessimistic assumption, but it's a realistic assumption. On that part of the database, things are skewed. So your assumptions are correct. On the uniform case, the maximum degrees have kind of lowered. So you're making, you're again using maximum degrees, but the maximum degrees are a lot smaller. So you're getting better estimates. Now you sum them up and you get better estimates. So they have essentially been offering optimizations to make these pessimistics, still pessimistics, but much more accurate, stuff like that. But they're all based on maximum degrees. So this is fundamentally the CEG that they use. Right. But let me, I think I understand. Maybe let me just come to this. So this is not our contribution. We kind of reproduced this in our benchmarks. This was done by another Sigmod paper in 2020, where they had shown, they had taken the Kai et al., the first pessimistic estimator, and compared it against a couple of optimistic estimators, and shown that they're very, very pessimistic. We kind of reproduced them too, like pessimistic estimators, if you just take them as is, are super pessimistic. Like they're a lot more pessimistic than the kind of this opt is essentially max. Okay, so that's the best optimistic heuristic. They're a lot worse than the optimistic ones. But we wanted to reproduce that. So, and advice is, despite, I'll be kind of contradicting the density papers, but my advice is still be optimistic. Like, I think it's a lot more practical. So use average statistics, but be pessimistic when you can, then try to be pessimistic and try to offset that. So that's essentially my position on.
So they're still overshooting with that pessimism.
Yeah, I think they're very overshooting, and to fix it requires a lot of computation. You can fix it with some of the optimizations that they have, but I don't find it very practical. You have to have like just for a single query, you have to maybe estimate queries over 1,000 partitions and then some, and that just is not going to be very practical, I think. I wouldn't do that in Inclusio or something. I wouldn't do that. I think it would be very slow. All right, so the most important question is this. Like what, you can define many CEGs, right? You can store a ton of statistics and, put them as edge weights, right? You could use skew statistics, right? You could use standard deviation of values as or coefficient of variation, which is mean over standard deviation, things like this as edge weights. You wouldn't really use them as extension rates, but they could be additional statistics to guide you select paths that are accurate, right? Or I think the most obvious thing is something like entropy, which is just sort of a statistic about how uniform things are. Again, you wouldn't use this as the extension rate. It doesn't make sense. It doesn't make sense to multiply with 0.2 or something. Like entropy is going to be between 0 and 1, but it could help you guide peak paths along with some other maybe optimistic statistics that you're putting, right? You could use different statistics, and then along with each statistic that you put on a CEG, you could use different heuristics, shortest, longest, random, right? This is the most important question. Now, I'm not too optimistic about that there will be a clean answer to this, because I think this is not easy to, like, there can't be a very clean answer that says that I can't imagine a paper that says these are the statistics that you should use. I think that's too strong a statement. Like databases, data column values could take all sorts of distributions, but I think some rules of thumbs can emerge. Like people essentially did experimental studies on this. So something like, avoid paths with large entropy edges, pick short top paths, things like this can emerge. I'm not going to work on this. So I'm done with having worked on this problem and seeing how hard it is to just, to me, it's super hacky, the things that we're doing in these systems. And I'm also not too hopeful that whatever you do, ML, whatever, I don't think there can be a very clean sort of, just the problem is too complex, I think. Just like estimating cardinalities of values is too complex. Probably the best, like clearly the good thing to do is just keep more statistics. That clearly helps. I think it's a no-brainer. And to pick good statistics, accurate statistics, maybe as the queries are executing, learn them and use them. That's the type of thing I think makes a lot of sense to me. But to assume that there will be this one CEG with great statistics, I think that's too strong. But I think people can essentially study a bit more. I hope that people study a bit more about and give some advice about, like, here are the paths that formulas people should use, or here are the statistics that we got good results on. I think that kind of advice can emerge from some other research. Well, I should stop. Wow, exactly on the time. I'm stopping now. Okay, so I'm not going to talk about quizzes. Thank you very much.